Let's think about continuity here for a minute. So right there, definition 2.1 says that a function f of x is continuous at a point A if the limit exists there and returns the same number as what the function gives you. So the function is equal to the limit. So you need a couple different things to be true in order for a function to be continuous. One, the limit has to exist. It has to give you a real number. And two, the function has to exist. And three, those two numbers are the same thing. So if any of those conditions are not met, we would say a function is discontinuous. And depending on which one of those conditions is not met, changes the type of discontinuity. We'll see that here in example 2.2. So h of x, I don't have the function definition there, so we don't know exactly what it is, but we do have the graph, and we'll just graphically look at this and see what continuity means to us. So h of x is going to be a continuous function everywhere. So no matter what x value I pick, it could be -7. If I look at -7, the limit as x goes to -7 is well defined, right? From the left and from the right, it approaches that y value of -5, and your function exists there and returns that value -5, right? Effectively, you can draw that without picking up your pencil, right? And I can do this. There's nothing special about -7. Same thing is true for, let's say, 5. When x is equal to 5, the limit is well defined. It seems like it approaches a y value of maybe 3. And the function returns a value of 3 at 5. Right? So basically, I can draw this curve without picking up my pencil. That's an exceptionally good definition for continuity, to think about it intuitively. If you can draw the function without picking up your pencil, the function is continuous. Where it gets interesting is talking about discontinuities. So let's consider f of x here. Again, we don't have the definition of the function, but we do have the graph. So let's look at this and find the places of discontinuities. So all of these x values, so anything on the left side of 5, the function looks like it's nice and continuous, right? You can draw this without picking up your pencil. So it's continuous over there, but here, when x is equal to 5, or sorry, when x is equal to -5, we do see that the definition of continuity is not met. The limit, first, doesn't even exist. As you approach from the left-hand side, you return -5. And as you approach from the right-hand side, you return, I don't know, maybe something 0.25, something like that, right? The left-hand and the right-hand side do not return the same thing. Therefore, the limit does not exist. And if the limit doesn't exist, then there's no way that this definition is satisfied, right? The limit cannot equal the function value because the limit doesn't even exist at -5. So we call this a jump discontinuity. Easy to remember because your function jumps at that x value. We also say that this is discontinuous at x is equal to -1. So there's x is equal to -1. And we can see that we have a non-removable discontinuity there, a vertical asymptote. So this is not continuous. Why does it fail this definition here? For the same reason, the limit does not exist there. From the left, you get positive infinity. From the right, you get positive infinity. So the limit of f of x as x approaches -1 returns positive infinity. That is not a real number. The limit does not exist there. Therefore, the function is not continuous. Right? Think about that. You cannot draw that without picking up your pencil. So this was a non-removable discontinuity giving us a vertical asymptote. Right? We've seen that in algebra. Now it's also not continuous over here when x is equal to 3. Let's think about why this definition here is not satisfied. So first, the limit has to exist, but here we do see that the limit does exist. From the left and from the right, it seems like I get a y value of 0.25, right? But either way, I get the same value from left or right. The limit is well defined. So the limit exists. What about the function value? Well, yep, the function value exists there too, right? When x is equal to 3, your function value returns 5. So back up here, this exists and this exists, but are they equal to each other? And no, right? The limit is 0.25. The actual function value is 5. Again, you cannot draw that without picking up your pencil. So it's discontinuous there. We call that a removable discontinuity.